Let's learn how to graph logs. What gets math teachers dancing? I'm going to let you think about that one. On our agenda, we're going to start by reviewing graphing exponentials because it's something that we know. Then we'll find the inverse of that exponential to work our way to a log. We'll graph the parent graph of a log and then use transformations to graph them and state the properties of the graphs. Let's get ready. You're just going to need a notebook and pencil. And let's start with reviewing how we graph y equals 2 to the x. So I'm going to pick some values for x, -1, 0, and 1. And when I plug in -1, I'm going to get the reciprocal, so 1/2. 2 to the 0 is 1, and 2 to the 1 is 2. I'm going to graph those. And we have our exponential growth. So remember that exponential growth has a y-intercept. It also has an asymptote that is a y equals type of asymptote, horizontal, so y equals 0. So let's try to get our way over to logarithms. And remembering that exponentials and logs are inverses of each other, we should be able to take this equation, y equals 2 to the x, and switch it to a logarithm equation. So remember how we find inverse? We switch x and y first and then resolve for y. So I'm going to switch x and y. And then we need to use our conversion. So we're going to convert, this is currently an exponent form. 2 to the y is the exponent. So I'm going to keep the base, so it becomes log base 2 of x equals y. And when I graph, I just like to have my y on the left-hand side. So now we're going to think about graphing y equals log base 2 of x. So when we're doing inverse and we switch our x and our y, we can do the same thing with our table of values. We can switch the x and the y. So I'm going to switch those points around, and then we'll talk about the graph. So I want to plot 1/2, -1, 1, 0, and 2, 1. And then we have a logarithmic graph. So you can see that what was my y-intercept has now changed to an x-intercept. What was my y equals asymptote is a horizontal. I am never going to be less than 0 here for x, so we now have a vertical asymptote, x equals 0. So exponentials have y and y, logs have x and x. That's one way that you can remember that. This right here is the parent graph of y equals log base 2 to the x. It has an x-intercept to start us out at 1, 0, and it has a vertical asymptote. Remembering that inverses are reflected over the line, y equals x, and every point is reflected over that. So you can visually see that logs and exponentials are inverses of each other. Let's look at the parent equation. Same thing that we've been seeing before. If a is bigger than 1, it's going to be vertically stretched. If a is between 1 and 0, we're going to say it's vertically compressed. B is going to have a little bit more power in this one. If B is greater than 1, it's the inverse of an exponential growth, which should make sense because that would come from something like 2 to the x, where my base is 2. If the base is between 0 and 1, something like 1/2, then that's going to be the inverse of an exponential decay. H is going to shift it left or right, and if we're shifting left or right, that means we're moving that vertical asymptote. So any shift in H is going to change our asymptote, and then K is just going to move it up and down. I want to show you the effect of A on the graph. So if you notice, all of these have log base 2. So I kept that the same, but I'm changing my A value. So I went 1, 2, 3, 4. So we're looking at the effects of A. If my base is 2, then it would be convenient to plug in a 2 here because we know that log base 2 of 2 is 1. So this, when x is 1, y is 1. If I plug in a 2 here, log base 2 of 2 is 1 times 2, and I have the point 2, 2. And then this is going to be when x is 2, we're at, oh, that's supposed to be at 2, 1. And then 2, 3, and then 2, 4. So you can see that on my graph, we had 2, 1 on the red graph, 2, 2 on the blue, 2, 3 on the green, and 2, 4 on the purple. So it really does have that effect of vertically stretching it. Let's look at the effect of B. So you can see that I changed my B and I jumped to 20 just for the effect. So when it has log base B whatever b is, that's handy to plug into your value. So when I do plug in 2 here, I'm going to get 1, and I'm at that point, 2, 1. So now I'm going to plug in 3 for x and get 1, and now we're on the blue graph. And I'm going to plug in 4 and get 1, and we're on the green graph. And then you can see 20 would be way down there. So that's what b does. Let's go back to our parent graph. So again, with a log graph, we have an original x-intercept and an x equals asymptote. And we would have arrowheads, and it's approaching our asymptote but not touching it. This is log base 2, so you can see another helpful point is the point 2, 1. So let's try to graph these using transformations. We have 2 log base 5 of x. Again, giving some thought what you plug into x according to what your base is, so we can try to do these without a calculator. So I'm going to start with 1. This is not being shifted left or right, up and down, so 1 should be an okay number. So when I plug in 2 log base 5 of 1, well, log base 5 of something equaling 1 has to be 0, so that's going to be 0 when I multiply it by 2. 2 is not very helpful. I don't know log base 5 of 2 off the top of my head, but 5 would be good. So if we do 2 log base 5 of 5, that is 1 times 2 is 2. So we have our x-intercept at 1, 0. We have 5, 2, and then we're going to draw in our logarithmic curve. My asymptote is x equals 0, and that's my x-intercept. If we were asked for a domain, that's going to be 0 to infinity, and the range is negative infinity to positive infinity. Let's try to graph this one. You can see I have the same start to the equation, but now we're shifting it up 4. So I'm going to start with 1 again, and when I plug in 1, that's going to give me 0. 0 times 2 is 0 plus 4. So now we're at 4, 1. So we had our original x-intercept, and now that's going to move up to 4. Because this is moving up and down, it doesn't change my asymptote, so I know I still have my asymptote at x equals 0. Another good value to plug in is going to be 5. So when I plug in 5 there, log base 5 of 5 is 1 times 2 plus 4 is 6. And we have another point at 5, about 6. And you can see our whole graph just moved up 4. Let's try this one. I changed the base to 3. I'm going to think about my transformations. This is going to move to the right 1 and up 2. So it would have started at the x-intercept of 1. So from there, I'm going to move up 1, right 1, up 2, and I have that point. So that point is 2, 2. Let's try that in our equation. So y equals log base 3 of 2 minus 1, and then plus 2. So this is log base 3 of 1. This is 0 plus 2, so it does work. It does equal 2. I moved it correctly. Let's think about my asymptote, and this is going to move to the right 1 when my asymptote was originally on 0. So that means my asymptote is also moving to the right 1, and it's at x equals 1. I have log base 3. And another good total value would be 3 to be in there. So in order for my parentheses to equal 4, x would be 1. So I'm going to try that one. When I plug in 4, 4 minus 1 is 3. Log base 3 of 3 is 1 plus 2 is 3. So we have another point at 4, 3. And another good value is if I could make that equal 9. So that would be 10 minus 1. So log base 3 of 9 is 2 plus 2 is 4. So it'd be somewhere way out there at 4. And we're going to come around like that. And let's try this. Notice my base. I couldn't do a fraction in Desmos. It's really 1/3. So we want to consider that. Base of 1/3. And we have x minus 4. So I want to think about my shift. So this is going to go to the right 4. I would have been at 0, and I'm going to the right 4, which means I should have a point at 5. So let's try 5 and see if we do come out to 0. So y equals log base 1/3, that's supposed to be a 1, of 5 minus 4 is 1. 1/3 to the 0 is 1, so that's correct. Let's use our transformation again to shift my asymptote. It was originally at 0, so now it's going to be at x equals 4. And another good value would be, well, if I have log base 1/3, another good thing for this to equal would be 3. So then x could be 7. So if x is 7, then we have log base 1/3 of 3, and we're thinking 1/3 to something equals 3. So that would be x equals -1, -1. So we're at 7, -1, and you can see it's going to come down my asymptote and then be the inverse of an exponential decay. So to recap, exponentials and logs are inverses of each other. That means the graphs are reflected over the line y equals x. Log graphs move the same as everything else. And log graphs start with an x-intercept and they have an x equals asymptote. Nice job.